You all are welcome for today's lecture. The module is Engineering Electromagnetism. This is a 3 credit subject. You can see in the module information sheet here. So these are the LOs, or what we call the module learning outcomes. And if you read this document, you can find what are the lecture outline. So this is the interesting part, the method of assessments. You have to score the 50 marks out of 100 under the continuous assessment by doing the 2 lab sessions, 1 mid evaluation, and the 2 take home assignments. Once you complete these continuous assessments, then you have to go for the end exam. Once you complete this continuous assessment, there's a requirement for that. You can see here, minimum 35 marks in continuous assessment, and then minimum 80% attendance for the lectures, and have to complete the all lab sessions. During this COVID situations, you have excuse for this uh, lab session, but the day will come you have to do that one. But firstly, during this period, we will try to complete the lecture part. So later on, we will conduct the lab sessions. The reason is to eligible to appear for the end exam, you have to complete the lab sessions. So in this document clearly mentioned that eligibility to appear the end evaluation is completion of the lab session. So once you complete this lab sessions also, you are entitled to do the or sit for the end exam. Those are certain approval things, so you can't bypass or we can't bypass. Those are some written requirements very clearly on the documents. Once you sit for the end exam, you have to earn 35 marks for the end paper. That means around 17.5 marks. You have at least score more than 17.5. If you score around 70 or something, then you are failed. Okay, so you are repeat student, you will be a repeat student. If you have good marks for the continuous, but if you score around 16 or something for the end exam, then definitely you are failed student. Okay, so keep it in mind that you can't happy. So the status will be changed once you score less than 70.5. So keep in mind that at least you have to score this amount for the end exam. And these are some recommended readings, especially you can find this book in the library. I will refer this book to prepare my lecture notes, and I'll refer this textbook to prepare questions also. So therefore, better to collect this book from the library. We have around 8 copies. Once you visit to the lab, university, you can collect this book. Interesting book. I don't know whether the PDFs are available, but if you try to search from the internet, sometimes you have a chance to find this document. So just search it, whether it's available in the internet. You have some technique how to find these things, or use that techniques and try to find this book. The reason is physically you can't collect this book by coming to the university. Therefore, better to find some PDF document on the internet and study it. I'll refer that textbook. Okay, I'll refer that textbook. This one represents the learning outcome, or we call the program outcome matrix, LO to PO mapping. So under this module, we are addressing, or we are trying to achieve this program outcome of these areas. So just refer this document. I have already sent to each students. In the morning, I send that email. So refer that document, you can get some idea. Just read. It's interesting, this document. Just read this one. So this is the lecture outline or module activity plan. Firstly, I will do this vector analysis part, then electrostatic and macroscopic part I will conduct. This part I will do. This one I will do. And this part also I will do. This time I have another module. Therefore, previously during last 10 years, I did the whole module, but this time this two part will conduct by Mr. Tilina, because I have to do the another final year module, microwave communication. Therefore, to share the workload, this time Mr. Tilina will continue this part. During last 10 years, I did this part. But this time, first time I will not do this part to workload balance. I had to share some hours for my colleagues. Therefore, Mr. Tilina continue these sessions. Then I'll go to the lecture. Yeah, you have this document, therefore you can refer it. I'll directly go to the today lecture without wasting the time. First of all, I had to do some basic things before I teach the electromagnetism concepts. The reason is this: most of the things are derived based on the mathematical background. With the mathematical computation methods, these all behaviors are described. Therefore, firstly, before I teach this module, what we call the engineering electromagnetism, I'll explain some mathematical things related to this module. First of all, this document also already have given to you. You can take a printout and read it very clearly. Everything's are described in this document. Therefore, you can easily understand. Okay, I will explain, but just read it, then you can understand. Firstly, I'll focus on the vector analysis. Basically, this vector analysis we can separate into vector algebra and vector calculus. Basically, we can divide this vector analysis into two areas called the vector algebra and vector calculus. In this section, we are focusing on the algebraic operation on vectors. In this area, under this vector algebra, we concern the algebraic operation on vectors. Under this vector calculus, we concern the differential and integral operations involved in the vector functions. Keep in mind that in the vector calculus, we are concerning differential and integral operations which are involving in the vector functions. So these two areas we are discussing. If you read this first paragraph, you can get some idea. As I mentioned previously, Vector is a mathematical tool which electromagnetic concepts are most conveniently expressed and best comprehends. As I mentioned previously, this vector analysis may be divided into two categories, which are called the vector algebra and vector calculus. This vector algebra concern algebraic operations, as well as this vector calculus concern on the differential and integral operations. So keep in mind that these terms. Various calculations or calculus operands we are studying here. Before we go for that one, firstly, we will see what is a vector field or vector and what is scalar. The quantities such as time, mass, temperature, charges, electric potential, energy, we call the scalars. Those are having only quantities, no directions, no directional elements. But when you think about this velocity, force, displacement, electric field intensity, flux density, those are having not only the amplitude but also the directions. The physical quantities which are having amplitude and the direction, we call those are vectors. Vectors. It consists of, as I mentioned previously, magnitude and directions. Magnitude and directions. On the other hand, you can say then scalar have only quantity, no directional components. For the scalars, you don't have directional components. You don't have directional component. Only you have a quantity, no directional components. So that's the difference in between vectors and scalars. As you know, you have heard that unit vector, the vector which magnitude is equal to 1 or magnitude is unity. Such vectors we call the unit vectors. I will refer this symbol to represent the unit vector. For example, just assume you have vector along this direction. Just assume you have vector on this direction, right? So if you want to find the unit vector along with this vector A, sometime your unit vector something like this. So here amplitude, the amplitude should be unit. This amount should be equal 1. This vector we call the unit vector. Okay, so unit vector along the A, this vector A. So you can find this unit vector. What you have to do, just divide this vector A by it is amplitude. This one represents the amplitude. This one represents the vector. This one represents its amplitude. If you divide this vector from its amplitude or magnitude, then you can find the unit vector. You can write down this one something like that. The vector along the A. This unit vector is parallel to the vector A. The directions for this unit vector is equal directions of the vector A. Only the difference is the amplitude. The amplitude is unity. So such a vector you can define as a unit vector. As a unit vector. Unit vector. Hope you are well aware with these things, but I remember these things. So keep in mind that if you have a vector, if you want to find a unit vector along the particular direction, what you have to do, just divide that given vector by its amplitude, then you can easily find the unit vector. Unit vector. Those are basic things. Then I will go to the new area. I just remind you what is a vector and what is a unit vector, because I will use these terms hereafter for my further explanations. This is new title for you. Hopefully it's new for you. Orthogonal coordinate systems. Orthogonal coordinate systems. What it is? As example, the Cartesian coordinates belongs to this orthogonal coordinate system. For example, this one represents x-axis, this one represents y-axis, this one represents the z-axis. This is one of the example for the orthogonal coordinate system. One of the example. To be an orthogonal coordinate system, these axes should be orthogonal to each other. As well as you can find some differential surface area on this xy plane. You can find some differential surface area on the YZ plane. You can find the differential surface area on the XZ plane. As example, you can write down this one dx, the differential amount. This one represents the dy. This one you can represent dy, and this one can represent dz. This differential length you can represent dx, and this differential length you can represent dz. So not only this xy z planes, you can see in here, these surfaces also orthogonal to each other. Look here, this direction and this direction, and if you build up, if you mark a direction perpendicular to this surface area, these surfaces also orthogonal to each other. This surface orthogonal to this surface. This surface area orthogonal to this one and this one also. Therefore, not only the axes, but also surfaces also sometimes might be orthogonal to each other. The surfaces or axes are orthogonal to each other, then we call such coordinate system orthogonal coordinate system. Orthogonal coordinate system. This Cartesian coordinate system is one of the example for the orthogonal coordinate system. Keep in mind that this one of the example. I will explain after this section cylindrical coordinates and spherical coordinate systems also. Those coordinate system also belongs to this orthogonal coordinates. Orthogonal coordinates. Right. Just read this paragraph. Just assume you have three axes, and then you can represent that axis something like this. Just assume you have a vector A. Okay. So just assume you have three axes which are orthogonal to each other. You can represent the unit vector along the one axis. This one represents the unit vector along the second axis, and this one represents the unit vector along the other axis. Just assume, for example, if it is XYZ, and then this unit vector is along the x-axis, this one along the y-axis, this one along the z-axis. So these are represent the unit vectors along the corresponding axes, along the corresponding relevant axes. By using these orthogonal coordinates, you can represent a vector something like that with the use of these unit vectors and these amplitudes. These amplitudes we are representing by using what we call the conversion factor into differential length. That differential length I will represent dni. You can get some idea if you refer the Cartesian coordinates. This dni mean dx. H we call the conversion factor. If your axes are represented by the length, then this conversion factor become 1. Keep in mind that sometimes your axis not the length, that axis not represent the length, it might be represent the angle. If it is a length, for example, if you refer the Cartesian coordinates, then your all axes are represent the length. Therefore, this conversion factor become 1. Keep in mind that. I know this is a little complicated, but once I select specific coordinate system like a Cartesian or spherical or cylindrical, then you can easily understand what I'm telling. But just try to familiar with this term, then again you can switch back to here and you can understand. I know now you are struggling what I'm telling, okay? So don't worry. This is general format, okay? I'll represent a vector with having a general format. When I represent these things, I'll refer this notation. As example, if you want to represent the differential length on your Cartesian coordinates, on your orthogonal coordinate system, what you have to do, if you want to represent length as a vector form, then you have to write down dl equal dl1 into unit vector along the one axis. This is along the two axis. This is third axis. This dl you can write down with the support of this conversion factor. This term we call the conversion factor into differential length. As example, if it is a Cartesian coordinate, this one represents dxo, dyo, dz. Okay. So for the Cartesian coordinate, this conversion factor h1 become 1, h2 become 1, h3 become 1. Don't worry, I'll explain later on. This is general form. Okay, I firstly represent general form. Therefore, differential length you can represent in this form. And similarly, differential volume you can write down dV equal dl into dl2 into dl3. Then what you can do by using this term, you can substitute this dl1, dl2, dl3. So dl2 you can write down h2 into dn2. dl3 you can write down h3 into dn3. If it is a Cartesian coordinate, this term represents dz. This one represents dy, something like that. Okay. This is general form or format to represent the properties related to the orthogonal coordinate system. And similarly, differential surface area you can write down by taking the product of dl2 into dl3. As example, if you have this type of axis system, right? So if you see that the differential surface area ds1 or something, this one represents the dy, this one represents dx. Therefore, the directions is along on this way for this ds1. Okay, for this surface area, directions is on this way. So these are also vectors. ds1, ds2, ds3 are represent the vectors. The direction for this surface area is z. Therefore, you have to multiply this amount by uz. So unit vector. As example, you can see here ds1. You can convert into vector form. Here just represent the amplitudes. So if you want to convert this differential surface area into the vector, surfaces also you can represent as a vector form. As example, this one. So just multiply this amplitude by the unit vector along the one axis. To compute the ds1, please look here. To compute this ds1, you have to take the product of dl2 into dl3. To compute ds2, you have to take the product of dl1 and 3. For the 3, you have to use 1 and 2. If you refer the 1 and 2, your direction is 3. If you use the 1 and 3, your direction is 2. If you use the 2 and 3, your direction is 1. Something like that. Therefore, generally, you can represent the differential surfaces as a vector form, as a vectors, by using these expressions. As example, ds z, you can write down h1 become 1, h2 become 1, dy, d, just dy and dz. You can write down this one. If it is Cartesian coordinate system, then this term become, I will explain later on, don't worry, D. I have done mistake, no? So, wait. As example, if it is a D S X, then this one become D Y into DZ, something like that. So if it is a DSY, then this one become 1 into DX and DZ, something like that. So this one represents general format. This differential surface area you can represent as a vector by using this expansion. If it is Cartesian coordinates, x, y, z represent the length. When your axes are represent the length, then these conversion factors of this h1, h2, and h3 become 1. Keep in mind that there might be some different orthogonal coordinate system. Some of the orthogonal coordinate system having axes, those are represent the length. There are some orthogonal coordinate system, not only they are represent the length, they are showing the angles also, especially in the cylindrical and spherical coordinate systems, you can experience this behavior. So this equation represents the general format for how to write the differential surface area in vector form. Now I'll focus one example. This Cartesian coordinate system is the one of the example for the orthogonal coordinate systems. To be an orthogonal coordinate system, the surfaces or axes are orthogonal to each other. If we satisfy this requirement, then we can conclude this coordinate system is an orthogonal coordinate system. Orthogonal coordinate system. Already I have given the lecture note, therefore this section only write down the lecture notes. You can refer, just take the printout and read it. Everything is clearly mentioned, therefore just read this document. That's enough. Then we can serve the time. Otherwise, I have to, given time is 3 hours, but within half an hour I can complete if I refer this note. That's my target. That's my target. No need write down. I will give the document very clearly. Otherwise, I don't know what you are writing. I will tell something, you are writing something else. Therefore, to make this initiation very solid, to give the best explanation with having good lecture note, I refer this one. Then you can build up the foundation with solid way. As I mentioned previously, Cartesian coordinates are one of the examples for the orthogonal coordinates. Cartesian mean that x, y, z plane. Already you are well aware of this Cartesian coordinates. Basically, I can represent that one something like this. You have 3 axes. This is one axis, this is another axis, and this is another axis. So this axis represent the x, and this one represent the y, and this one represent the z. The unit vector along this direction is I'll represent as the ux, and unit vector along this y-axis I'll represent the uy, and unit vector along this axis I'll represent the uz. This ux, uy, uz are the unit vectors along the corresponding directions. Here, this xy z represent the length. X, Y, Z represent the length. If your axes are represent the length, keep in mind that the conversion factors of H1, H2, H3 become 1. This one H1, this one H2, this is H3. Here I'll use X, Y, Z. Therefore, rather than writing 1, 2, 3, I'll use here X, Y, Z. Okay. Therefore, keep in mind that if it's a orthogonal coordinate system, and then those axes are represent the length, at that time keep in mind that your conversion factors become 1. Therefore, related to this Cartesian coordinates, you can represent the differential arc length in this form. Here you have another term. What it is? Hx. Here you have another term. Hy. Here you have another term. Hz. Those terms become 1. Therefore, differential arc length, you can generally write down dx into ux is a unit vector, uy unit vector, uz is unit vector. So this is the procedure how to represent the differential arc length with respect to the Cartesian coordinate system. Cartesian coordinate system, right? Similarly, you can write down differential surface element, something like this. This ds is here. This is the differential. Sorry. Just wait. This one represents the, let me do this one. This one represents the, this differential surface area, right? And this differential length you can write down dy. This differential length you can write down dx. Therefore, this one represents the dsz. The direction for this surface we define on this way. This is the direction. That direction is perpendicular to this differential surface area. Keep in mind that this is perpendicular to this surface area. This one represents the directions parallel to the uz. That's the point. For the Cartesian coordinates, as I mentioned previously, you have that h1 and h2 also. Here, that h1 become 1, h2 become 1. Therefore, you have a simple equation. Simple equation. And similarly, now you can guess where this differential surface area is located, where this dsy located based on this explanation. Am I correct? Can you guess? Can you guess where this dx, dsx and dsy? Yes, of course, you can do that. You can do that. As example, this one represent which one? Can you guess? This differential surface area represent this one. The direction for this surface we define along the y-axis. This is the axis that is perpendicular to this selected differential surface area. This one represents dsy, right? These surfaces also, these differential surfaces also, keep in mind that orthogonal to each other, right? These surfaces also orthogonal to each other. So I have a message for you. I can't take a physical attendance. Therefore, what you can do, just put your registration number for the chat box. You can find the chat box. Please write down your name and registration for the chat box. Then I can find already 64 students participate for the lecture. So as attendance, I'll take this one. Please just put your registration number and the name to the chat box. In addition to this differential surface area, I can define the differential volume on the space. Differential volume on this space. As example, you can find this type of volume on this space. Differential volume, right? Something like this. This one represents the dV. This one represents dV. You can find the volume by using this expansion. So this is not a vector, okay? This is scalar. This scalar, you don't have a direction. So differential volume you can write down dx into dy into dz. This is the way how to define the differential volume element related to Cartesian coordinate system. Cartesian coordinate system. Just read this document, then you can get some idea. Let's see the next orthogonal coordinate system we call the circular, or we call the cylindrical coordinate system. Some people use this on circular cylindrical coordinate system. Before I explain this one, I'll refer some good picture, but I'll see that this is good or not. Yes, I'll draw picture to get some idea. Yes. Just give me 1 minute to make some enough space. I will select this type of axes. Just assume I have 3 axes. This is the procedure how to define the circular cylindrical coordinates. I will show you. Here, to locate this point, I'll refer this type of procedure. Right. This is the procedure. In this system, to locate this point, to identify or express this point, I will use one angle as well as this radius I will refer, as well as I will refer this height of this edge. I will refer these parameters. Z, R, and phi. By using these three parameters, I can define any points on this space. This is the point P. I can define exactly this point with the support of Z, R, and phi. Here, this is represent one unit vector. This one represent one unit vector which is parallel to R. This one represents the UR. Here I will define another unit vector along this axis. This one represents the UZ unit vector. I will define another unit vector tangent to this point. Sparshia, tangential. This one represents the U phi. Here you can see R is a length, Z is a length, but phi is not a length. Therefore, conversion factor for this one equal 1. For this one also H equal 1. But this one we don't know. So we will see how to find that one. I will write down this length as a dr. I will write down this differential height by using dz. As you know, this is d phi. Then this differential angle, I will represent d phi. Then if you know this distance, this one represent r, this one r. Therefore, this length you can write down r into d phi. As you know, S equal r theta concept you can apply for here. This one measuring in radian. If you measure that one in radian, then this arc length you can write down r into d phi. Then keep in mind that this term become a conversion factor for phi. For this h, this one h1, h2, this h3, then this conversion factor represents this r. Okay, here in this cylindrical coordinates, in cylindrical coordinates, you can represent the any point by using three parameters, r, z, and phi. With the support of this three parameter, r, with the support of this three parameter, r, phi, and z, you can express any point on the space. This concept we call the cylindrical coordinates. Cylindrical coordinate. Look here, in cylindrical coordinates, you can write down a vector by using previous format. So here, unit vector along the r, this is unit vector along the phi, this is unit vector along the z axis. So with the support of these three unit vectors, you can represent the vector with respect to this circular or cylindrical coordinates. As I mentioned previously, r and z represent the length. Therefore, conversion factors for this r and z, 1 for the phi represent the angle. This term become the conversion factor. This r, this one represents the conversion factor. Keep in mind that how it's happened. You have to memorize this one, okay? So read this document, then you can get some idea. I'm explaining for you, but read it. Then it's interesting. Therefore, differential length dl, previously we wrote h1 dn1 into un1 plus h2 dn2 into un2 plus h3 dn3 un3, something like that. Your r is represents the length, therefore this one become 1. Your h2 also, sorry, your z represent the length, therefore this h3 become 1. But this phi represent the angle, therefore your h2 represents some conversion factor, h2 equal r. Therefore, differential arc length, you can represent something like that with respect to this cylindrical coordinate system. Cylindrical coordinate system. And similarly, you can write down this differential surface areas also. Can you guess where this surface? Can you guess? This surface represent here. This is the surface. Direction is along the arc. Assume you are measuring R. You are measuring R on this way, right? This is the direction for the R. This is the direction for the UR. This is the direction for the UR, right? Therefore, DSR represents this red color surface. Similarly, can you guess what is this surface? Can you guess this one? The direction for this surface we define along this way. Along this way. This is the direction. Along this way. That means this is the surface area we are interested. Sorry. D. Yes. This is the area. This one represents this surface area. And this one represents this surface area. Something like that. Therefore, you can write down these surfaces by using this form. This surface area also orthogonal to each other. These surface areas also orthogonal to each other. Similarly, you can write down the differential equation for the differential volume element by using this dr. You have dr, you have dz, and you have r d phi. By using this length, differential length, you can write down the differential volume. Okay, so this is the idea. So tomorrow we have another lecture. I will continue this one. Tomorrow I'll continue this one. Please read this document already have given to you. Please read this document. From next week onward, this today 1:30 lecture I will take from the 7:30 to 8:30. Okay, from next Monday onward, I will take this 1:30 lecture to shifted to the 7:30 to 8:30. If you have any problem, please let me know. Next Monday, I will do this lecture from 7:30 to 8:30. This is a little bit tough subject, therefore best time to do in the morning time. This time is not good. This is a eat after eat. You may feel some sleep. No? So better time is in the morning. This is a little bit hard tough subject, difficult subject. Therefore, I'll use next Monday 7:30. If you have any problem, let me know. Tomorrow we'll meet and we'll continue the next. Have a nice day.